Everyone, in the previous lecture we have discussed about zero order reaction, the integrated rate law for zero order reaction. Now in this lecture we will discuss about first order reaction and the integrated rate law for first order reaction. So first order reaction, first order reaction. The general rate law for first order reaction is RA is equal to KCA1, where N show that it is the first order reaction. Here the rate and concentration are directly related. The rate and concentration are directly related in the first order reaction. Now, as we know that rate of reactant is equal to change in the concentration of A with respect to time. It is rate of reaction with respect to component A, and rate is equal to, for first order reaction, rate is equal to KCA1. Here we have written it. So this is the rate for first order reaction. Now as we know that rate is equal to minus dCA divided by dt is equal to KCA. Now we will use these two equation, minus dCA divided by CA. For integrated rate law we will rearrange this equation. So minus dCA divided by CA is equal to KDT. Now integrated this equation, suppose this is equation A. Now integrate this equation A. After integration we will get minus dCA, integrate both sides of equation A, we will get, now at time t is equal to 0, concentration of A is Ca naught. Now at time t is equal to t, at some time the concentration will be Ca, and this is the minus sign. So we will write it again, minus dCA divided by Ca is equal to K dt, and we integrate it. Time t is equal to 0, the concentration was Ca naught. At time t is equal to some time, time t is equal to some time, the concentration is Ca. Now after integration we will get minus ln Ca, and applying limit we will get Ca naught into Ca, and it is equal to t minus 0, initial time and at time t. This is initial concentration, this is the final concentration. Now after applying the limit we will get minus ln Ca minus ln Ca naught is equal to K T, minus ln Ca minus Ca naught is equal to K T. Now multiplying both sides of this relation by minus, so ln Ca minus Ca naught is equal to minus K T, and it is ln Ca divided by Ca naught is equal to minus K T. Now in the power of E we can write it E, both sides we apply the E exponential relation, this will become this, and we will get Ca is equal to Ca naught e to the power minus K T. This is the integrated rate law for first order reaction. This is the initial concentration, this is the concentration at some time, this is the time, this is the rate constant, and this is the exponent or irrational number 2.71 irrational number. So this is the exponential law, which is Ca is equal to Ca naught e to the power minus k T. Now the half-life for the first order reaction can also be written as at time t is equal to 0, Ca is equal to Ca naught. Ca is equal to Ca naught. Now at time t is equal to half-life, which is t into 1 over 2, Ca will become, initial concentration will become the half of the initial concentration. The Ca will become Ca naught divided by 2 at the half-life. So Ca will become Ca naught divided by 2. This Ca will become Ca naught divided by 2, and which is equal to Ca naught, which will be equal to Ca naught e to the power minus k T 1 over 2. Now this cut with this, and we will get 1 over 2 is equal to minus e k into 1 over 2. Now we get the relation 1 over 2 is equal to e to the power minus k T 1 over 2. Applying ln to both sides, 1 over 2 is equal to minus k half-life ln of e. Ln of e is equal to 1. That is a mathematical rule. Now ln of 1 over 2 is equal to 0.693 minus 0. It is equal to minus k T 1 over 2. This cancel with this, and the half-life from this relation is equal to 0.693 divided by k. So the half-life for first order reaction depend on the rate constant. Increase the rate constant, it will be decrease it, the half-life will be increase, and this is the constant value, and it is equal to ln 1 over 2. So this is all about the first order reaction, the half-life for the first order and the half-life for the first order reaction. Ca, we also graphically we can also written this equation is, it is equal to Ca naught e to the power minus k T. Now at time t is equal to 0, Ca will become Ca naught. Now at higher time, for example if time tend to infinity, then what will be the Ca? So Ca will be equal to Ca naught e to the power infinity, and e to the power infinity is nothing but it is also infinity, and anything divided by infinity is equal to 0. So at higher time, or when time tends to infinity, the Ca will become 0, but at the start Ca is Ca naught. So we will get graph like this. This is the time, this is the Ca. At time t is equal to 0, Ca is equal to Ca naught. Suppose this is the Ca naught. Suppose this is the Ca naught, and at higher time C tend to, this is the Ca naught. At time 0, this is 0 time Ca is equal to Ca naught, and at higher, when time tend to infinity, Ca become 0. At higher time Ca become 0. So this is the graphical form of the first order reaction. Thanks.